Alrighty, greetings everyone. Today we're going to be talking about the geometric distribution or the geometric model. We know the normal model. Here's another model we can use. And this one's fairly specific, as you will see. This is considered one of the Bernoulli models, and based on Bernoulli trials, this was given to us by Daniel Bernoulli, who was a relative of Jacob Bernoulli, who gave us the central limit theorem. So this was a brilliant family of mathematicians from way back in the day, and they gave us a lot of important formulas in math and physics and apparently probability. So imagine a situation that has these following conditions. The trials are independent. Each trial can result in only two possible outcomes, success or failure, and the probability of success is fixed. It's the same for all trials. So situations like this happen all the time, like flipping a coin or looking for defective products rolling off an assembly line, shooting free throws. So anything that basically has a yes-no, success-fail kind of response to it could be a Bernoulli trial as long as we have these other conditions. So the geometric is a special one, and I call it the wait time distribution, where you're waiting for the first success. That's how you know it's geometric. The variable is defined as let x equal the number of trials until the first success is observed, including the success trial. And so when you read the problems, you'll read something like, what's the probability that the first home run is on the fourth pitch, or something like that. So that's you're waiting for the first success. Here's your book's presentation of the formula, and they also give us the expected value and standard deviation formulas. But the main formula is this one here, the P of x equals q to the x minus 1p, where P is the probability of success, Q is the probability of failure, and then that X is the number of trials until the first success occurs. You'll see this in the examples. It's actually super easy to understand, but we first need to talk about independence. So one of the requirements for Bernoulli trials is that the trials be independent, and this is going to be an important idea moving forward in the course. So if I can pick out the important ideas out of this couple of paragraphs, they talk about how when we were looking for Tiger Woods cards in a box of cereal, we said that the probability that we find a Tiger Woods in one box has no effect on the probabilities in the other boxes. And they acknowledge here that this is almost true. Technically, if exactly 20% of the boxes have Tiger Woods cards, then when you find one, you've reduced the number of remaining Tiger Woods cards. So you've changed the probability that the next one is a Tiger Woods. For example, if you knew there were two Tiger Woods cards hiding in the 10 cereal boxes, then finding one would clearly change the probability that the next one is a Tiger. With a few million boxes of cereal, though, the difference is hardly worth mentioning. So if we had an infinite number of boxes, it wouldn't be a problem. It's selecting from a finite population that causes the probabilities to change, making the trials not independent. So we have a rule of thumb, though, for these in-between cases, and it turns out that if we look at less than 10% of the population, we can pretend that the trials are independent and still calculate probabilities that are quite accurate. So this little thing highlighted in yellow is super important. It's the 10% condition. And we will be using this for the rest of the year because very often the formulas and ideas that we use require independence, which we cannot verify. But we can say that if the sample is smaller than 10% of the population, we can proceed as if the trials were independent. So this will become kind of a mantra for us. You'll see this on most problems in the second half of the class, for sure. Before we look at a couple of examples, here's a note about the calculator. If you think about finding the normal CDF, for example, we go to second distribution, and there we see normal CDF. Remember, the CDF is a continuous density function. It comes from the left. We don't use the normal PDF, but we could use the geometric PDF because that just calculates a particular value. Like if I wanted to know the probability that the first success was on the 7th trial, that would be PDF P, whatever that probability of success was, 7. The formula is so easy for just individual probabilities like y equals some value that it's not worth using the PDF formula. The CDF, though, can be very helpful because the CDF sums a bunch of probabilities coming from the left. So you'll see this in the examples here. Okay, first up, let's see if this scenario that's described here is even a geometric setting. If it is, let's define an appropriate geometric random variable. So, example A, we shuffle a standard deck of playing cards well, and then we're going to turn over one card at a time from the top of the deck until we get an ace. Is this geometric? Well, we're going to be turning cards until we get an ace, so it sort of feels geometric. It's a wait time situation, but remember, one of the key facets is this idea of a fixed probability of success. So in this case, we have the two outcomes. It's either an ace or it's not an ace. But since we're drawing from a single deck of cards, the probabilities are changing as we draw. So the probability that the second card's an ace, given that the first one was or wasn't an ace, is not equal. So these are not independent events, not geometric. Okay, here's another one. Larry likes to shoot a bow and arrow in his free time. On any shot, he has about a 10% chance of hitting a bullseye. He's bored to tears, and so as a challenge, he decides to keep shooting until he gets a bullseye. Okay, so first thing to notice is he's going to shoot until he gets a bullseye. That's a wait time situation. We're waiting for that first bullseye. It looks like we have a fixed probability of success, and the only outcomes are he makes a bullseye or he doesn't. So as far as the independence issue goes, we can presumably assume independence here. I mean, in any type of a performance event like this or shooting free throws, for example, people now argue that those are not truly independent events because there's this whole psychological interference that kind of creeps in, whether you think you're going to make it or whether you think you're not. So it's really hard to really argue that those are independent, but the classic textbook approach to this is that they are. So yeah, these are independent. So we can define an appropriate geometric random variable would be, yes, let x be the number of shots required to hit the bullseye. Okay, let's look at an example where we get to actually use the formula here. So, cranky mower. To start her old lawnmower, Rita has to pull a cord and hope for some luck. On any particular pull, the mower has a 20% chance of starting. Find the probability that it takes her exactly 3 pulls to start the mower. Show your work. So there's the formula, and it looks kind of daunting. It's got x's and x's and q's and p's and super easy formula. Here we're looking for the probability that x equals 3, random variable x equals 3, meaning the first success happens on the 3rd try. So using the formula here, q is the probability of failure, where the probability of success is 0.2. So this is going to be she failed twice and had her first success on the 3rd try. So the probability that x equals 3 is 3 minus 1, which is fail to the 2nd power, and then this wait time, we're waiting for a success, happens on the 3rd one. So fail, fail, success, the first success is on the 3rd one. Super easy. Don't let the weird formula-ness scare you on this. Very easy stuff. Okay, let's see. Find the probability that it takes her more than 10 pulls to start the mower. Show your work. Okay, let's see. The probability that x is greater than 10 means that it didn't start until the 11th pull, or maybe the 12th pull, or maybe the 13th pull. And all of those probabilities would have to be added. So maybe the mower doesn't start until the 76th pull. That's the thing about wait time probabilities. Theoretically, they could go on forever. So we obviously can't calculate that the way it's written, but what we can do is realize that the probability that x is greater than 10 is 1 minus the probability that x is less than or equal to 10. And that less than or equal to 10 probability is what the geometric CDF gives us. It's going to take the probability that x equals 1 or 2 or 3 or all the way up to x equals 10 and add those up. So if I take 1 minus these CDF probabilities coming from the left, from 1 to 10, I get that answer there. It's really quite simple. You could try that on your calculator and see that you can do this. And yeah, calculator is definitely your friend in these less than or equal to situations. Okay, here's another example. It might make this a little easier to see. So Marty decides to keep placing $1 bets on the number 15 in consecutive spins at the roulette wheel table until she wins. On any spin, there's a 1 in 38 chance that the ball will land on the 15 slot. So notice this is geometric. We've got a fixed probability of success, which is 1 in 38. There's only two outcomes, success or fail. It's either a 15 or it's not. And the spins of the wheel are independent. So would I be surprised if Marty won in 3 or fewer spins? So first I'll show you the computation without the calculator. The probability that x is less than or equal to 3 is, well, she won it on the first spin, or she won it on the second spin, or she won it on the third spin. So this first one isn't super helpful here, but it's just showing that there weren't any duds. She just won it on the first spin. On the second spin, we had one miss, and then we hit on the second one. Or the probability that x equals 3 is, we had 2 failures and then 1 success. So you add those all up, and you get a probability. Now to do this on the calculator, all I would really do is just go, this is going to be geometric CDF, and the parameters you put in are P and then X, or K they call it sometimes. So the P you can put in as a fraction, 1 divided by 38, comma 3, and then the calculator just spits that out really fast for you. Now as far as the question, would I be surprised? Well, it looks like there's about almost an 8% chance that this is going to happen. So would that surprise you or not? You can answer yes or no, just base your answer on this 7.69%. We'll talk more about that. I'm watching the clock here, guys, because the free version of this lesson recorder poops out at 15 minutes, so I only have about a minute. I think the remaining example is this one, which is just an expected value problem. How many spins would I expect it to take until Marty wins? This makes sense because the formula is 1 over P. The probability, P, is 1 over 38. 1 over 1 over 38 is 38. And it just kind of makes sense that it would take, as a long-run probability, 38 spins to win something that has a 1 in 38 chance of winning. So hopefully that's kind of intuitive. Don't have a standard deviation example for you. We might run into one of those. We'll try to pay attention to it when we do. Haven't seen that too much out in the wild, TBH. So, okay, about 1 minute left here, so let me throw this out there for you. Please give this a try. It's just a handful of geometric probabilities, and it's good practice. And yeah, so if you have any questions on this, shoot me an email. Otherwise, thanks for watching, and when we come back together on Thursday, we're going to not spend a whole lot of time on this, so you'll want to do this on your own. All right, you guys, thanks much. Good luck on the quiz, whichever day you're doing it. If you've already done it, good luck past tense, and we'll see you soon. Bye.